Discussion is going to be led by Roman and Julian. Tag team, or I was going to do this.
Okay, so we came up with a list of questions, which is kind of based on the talks we had today, but a few talks were not related to simulations. But nevertheless, I think we have a pretty long list of questions, so we managed to put the most important one at the top, I think. So I suggest we go down the list, and so I'm going to read you the question. You're not going to see them here. And I suggest we start talking about the questions, and if there is no comment at all, then we move to the next one, right? And pretty much it. Any comment on the methodology? Okay, good. So the first basic question we came up with, especially in light of the last talk, actually. Do we think collectively that we are missing some important physical processes in galaxy formation? Today we've seen a lot of exploratory studies regarding MHD, radiative transfer, cosmic rays. Basically, do you think, according to your personal opinion, that we really need to worry about missing bricks in our constructions, and if so, what should be the priority? You're up. So my personal opinion would be MHD, but I gave a talk already on that, so I'm not going to do it again. But if anybody has a comment on that, do you think we all should be happy with what we are doing now? Or?
Well, I think maybe we should rephrase the question. I mean, of course, humanitarian fields may be important, other cosmic rays may be important, and so on. But I think we should really figure out, how the, supernova feedback works really well. And so so it's not just putting in more and more and more in a kind of crude way, but I think really, these kind of simulations where, we have stratified media and you look really what does the supernova feedback does, and then we'll use these really kind of, extremely high resolution simulations to inform, galaxy formation simulations, I think is maybe the right way to do it.
But let me make a provocative answer. All physicists, what they try to do is to isolate the dominant physical process, and they completely ignore all the others. It's a good physicist does that. And maybe we're fooling ourselves believing that supernovae are the dominant process. Maybe it's something else, right? Maybe it's cosmic ray, magnetic field, you name it, right? So I agree with you that, supernovae are poorly understood, so we need to work more on that, but maybe we're just on the wrong track here.
I agree with Roman that I think there are different processes related with star formation that are happening at different time scales. I want to take into account any of those, in particular the effect of radiation from these very massive stars that they live only a few million years. And in the first years of the formation, they have a huge impact in the surrounding medium, just before any supernova explosion.
Yeah, on this I'd like to add a comment, is there's something even more worrisome, is that we might find a way to do the supernova properly, but what if radiative transfer for massive stars actually couples to that and makes it more efficient? So we have to worry not only about getting, one physical process right, but there might be strong nonlinear coupling between the two that might be important to get.
Let's move to the second question.
Second question. So the second question is about simulation strategy. So we've seen a talk by Andrew, and so that advocated for a genetically modified approach where you would combine all the good points, or in as much as possible, as all the simulations. So the question was, do we think we have the good strategy for going around this problem? How many, large periodic boxes versus zooms versus isolated simulation do we need? Do we have to worry about halo selection strategies when we do the zooms? What is this telling us about, the representativity of what we're doing?
And to elaborate on that and trigger some reactions, maybe, I think a very interesting comment was made about the occurrence of clumps. I immediately raise your interest. Because if you select halos which, for some reason, right, by luck or by lack of thereof, are, especially at the redshift you're looking at the results, are correlated with a very strong accretion rate, you may be in a favorable situation to form clumps. And then if for some reason a lot of your simulations are like that, you may conclude that all galaxies have clumps. While on the other hand, if you're driven by other consideration, if you select halos which form early and then have a very low accretion rate in average, like I think one of Robert's halos has been picked up like that to build a dead galaxy, then you're in a situation where the probability to have clumps is lower, right? And so I'm just want to, I'm a bit worried, or maybe I'm wrong, but I'm a bit worried that we might introduce some bias, which together with observational bias might just make the whole picture wrong.
Just on the clump story, I tried to emphasize this morning, and just in response to what you said, I'm afraid maybe you didn't get it, so let me just repeat. Forgetting the simulations. The observations are totally clear. We've looked at over 100,000 galaxies in candles. Clumps are found in more than 60%, more than 50% anyway, of all star-forming galaxies at redshifts 2 to 3, in the mass range of 10 to the 9 to 10 to the 11 solar masses. They are ubiquitous. If your simulations do not show them, and these are massive things, they're 10 to the 8 solar masses typically, your simulations are missing some essential ingredient. It has nothing to do with picking the right halos. Once you've done enough halos that you've got a few that are rapidly accreting, I agree with you. Of course, if they're not accreting, they're probably not going to form clumps. But once you have a few halos that are accreting, if they're not forming clumps and they're not showing the compaction process, then you're missing something really crucial. Crucial in the observations.
So I'm happy I raised your interest. But I think you told a key word here. You say star-forming galaxies.
Yes.
So this is a well-defined.
That's a majority of galaxies in that mass range at those redshifts.
Yeah. But what I'm saying is that there are various degrees of star formation intensity, and depending on what you have in mind, or depending on observational bias.
I mean the ones on the main scene.
Yes. Okay. I'm not an expert in observation, so I have no idea how complete or incomplete this view of the universe is. But that's since I'm more on the simulation side, I know the dirty details, and I'm worried that we might introduce biases. Okay, regarding clumps, go ahead.
I was going to go to not clumps. I was going to go back to the broader question. So if you want to do clumps, do you want to do clumps or not clumps? I was going to your first. I was going to your actual question. Yeah. So I was just going to say. I mean, it's at the risk of stating the obvious, but the kind of simulation that you want to run depends on the kind of question that you're asking, right? And the only thing that we should be wary of is asking the wrong questions with the wrong simulations. But in terms of the actual mix of simulations you choose to do, I think you just have to make a personal choice depending on what kind of things you're asking. And certainly for the GM stuff, I'm not suggesting everybody has to suddenly switch and do that. It's just another thing you can do.
Yeah, but I was wondering how much you can, so let me rephrase slightly the question, how much you can transport results from one technique to the other. For instance, if you learn something about a mechanism in the isolated simulation, how much you can port that to cosmological simulations, right? Or zooms or whatever, What is because that's one thing we want to do. In the end, we want to learn from the simulations that are able to resolve some galaxy physics, and then move on to cosmological simulations when we don't resolve this, but we can implement the results as subgrid and then get large samples.
Right.
Eventually, that's what we want to do. The question is, in order for us to be able to do that, we need to know how much the results are portable from one type of simulation to the next.
Right. Well, we need to make them portable, right? If you look at the demands something like Euclid or LSST or whatever is placing on the kind of accuracy you're going to need to get reasonable cosmology, we have to make these things portable. And to connect to the question you had before about feedback, when you go to those big cosmological boxes, I mean, who cares about magnetic fields in those, really? I guess, everything's just going to be degenerate with just dumping pressure in. So you just want a recipe to dump pressure in that works and reproduces the results from actual simulations where you actually resolve physics. So I think as long as we maintain clarity about this, then we should be able to do it, right?
I'm pretty sure we're never going to do cosmology with, detailed galaxy formation physics. If that's what you're implying, it's.
No, I'm implying the opposite. I'm saying that you have some effective prescription.
If you're interested in cosmology, yes. Yeah, but in this room, nobody is interested in cosmology. We don't care about omega matter and whatever. So, okay, any more comment on that? So we have one more question for clumps, so we can get rid of clumps once and for all if you want. I have the feeling, especially regarding one of the last talk by Valentina, the talk from Valentina Tamburello, that there is a consensus that we more or less understand clump formation, at least from the simulation side. And we agree on their size, on their mass, on how it depends on the host galaxy parameters and so on and so forth. So, of course, these environmental properties can vary a lot depending on the feedback that you put in and so on and so forth. But for a given type of galaxy with a given velocity dispersion, gas mass, gas fraction, stellar mass, and so on and so forth, I think we all agree about the typical spectrum of mass we're supposed to find, and so that's a question I'm asking. So, do you think that we understand clump formation or not, or is still there's a debate and discrepancies between people? Again, numerically, in simulation.
I think we do not understand the formation of clumps in cosmological simulations, and we had several talks which describe the confusion we are having right now. We used to think that two-way instability analysis is perfect, and we wrote many papers predicting things, nice things from that. But recently we realized that two-way analysis is only a first approximation. The Q parameter is well above unity in proto-clump regions. So at the moment we are still puzzled, and we are entertaining many different possibilities, including turbulence analysis that Florent Renaud alluded to, and other ideas that we have in mind. So I don't think the dust has settled at all. I think there's a very interesting theoretical challenge there to understand clump formation.
Eugene?
So I just want to talk about the clumps from the observer side. So we spend a lot of time to discussing clumps in the simulation or theoretical models, but the key question is how can we compare those models to observations? So I have a feeling that the clumps you guys are talking about here is not the clumps that we are actually observed in images or in the reality. So you guys are more likely to talk about the small gas clumps, but eventually we have to go back to broadband images to look for clumps. Those are young star clumps, and how can we compare your result with our observation? So that's why in my talk yesterday I tried to persuade everybody try to observe your simulation, because only so that way you can compare your simulation, observe your simulation. You can compare your simulation with the observations. Otherwise, we don't know how to test whether the model or simulation is correct.
Any other comment on clumps, or that's it? We're rid of clumps forever.
I don't think you're rid of them forever.
Oh yeah? You think they're going to come back?
They persist in nature, so the challenge has been laid down by I Ching.
All right. Okay, so I'd like to bounce back on the next question, which Avishai alluded to, is the new star formation recipe. We've heard many talks about turbulence and how molecular cloud that form stars are known to be supersonically turbulent, and yet most of the recipes that are used in current simulations is just a simple density threshold. So do we think there is a need to go beyond that and implement this turbulent recipes and study what different it makes, or do we think that we're doing well enough with just the standard recipes? I'd like the guy that talked about turbulence to comment on that. I'm looking at you, Vadim.
I wouldn't talk about this, if I didn't think that it's not worth implementing, because, we can see that it can vary, but we can easily implement it in our simulations, but not do this. We're trying to implement as good physics for feedback. However, we sweep under the rug the star formation thing. Why do we do so?
Exactly. So I think Robert just mentioned that we should understand better supernova feedback, which is probably the first historical feedback process we came up with. But actually, before that, we need to worry about star formation itself, which will give the seeds for every feedback processes. And I think there is a wide discrepancies between all these new star formation recipes that are discussed, like your talk or Florent Renaud talk, or what they do in the fire simulation, which is a virial-based star formation criterion, and this has a dramatic effect on how feedback works. And so I think it's a worry.
I just wanted to be provocative and ask, when you ask these questions, do you also, or you and your colleagues who do simulations, think of metrics to discriminate the various possibilities against observations so that you can have some insight and tell us some insight or not?
You want to answer that? Just say no.
Of course.
Fantastic! And would you like to share them with us?
So I think what is interesting in those new star formation recipes is that they are calibrated to the Kennicutt relation. And I think the old way was to calibrate on the mean Kennicutt relation, and now those new techniques, based on turbulence, they're trying to calibrate on the mean, but also on the dispersion. And so basically you're looking at higher order moments, so to speak, of the Kennicutt-Schmidt relation, and you're trying to demonstrate that you're capturing the physics better, right? It's a long way, but that's the best we can do, collectively.
Yeah, actually it's not calibrated on like these observed relations. It's calibrated on physical simulations of turbulence, and apparently it gives the results which consistent with the observed relations. But in the first place, it was not correlated to produce them. So it's kind of interesting that it can be done.
So I like to think of it a little bit differently. Ultimately, we're never, ever, ever going to do a simulation that has every physics in it from core principles, from quantum mechanics. So at some point, we're going to have a subgrid level where we go below which we're not going to actually implement the physics. And all we need to do is decide on what scale are we going to do that. And to some reason, do we actually really want to resolve the GMCs? Or do we just want to say, no, the GMC scale, we're not going to go below. We have empirical evidence. We know what the effective star formation is coming out of a GNC. We just need to think about how do we implement the feedback on that scale. And that's a hard thing. We think we know. I think the only reason why people are interested in actually going to do the actual turbulent GMCs and the supersonic turbulence in the GMCs is because if we want to implement supernova feedback at the sort of more base level, then that's what's needed. We need to resolve that structure. But ultimately, once we've done a few of those simulations, then maybe we can go back to the simulations. We don't need to reach that scale at all, and ultimately just put in what we've learned, what happens on the scale of a GMC or larger. I mean, we're always going to have subgrid physics. All we need to do is decide on what scale we're going to stop.
But do you really think we understand even GMC physics enough that you might confidently say, no, okay, this is enough, I don't need to go any further there? No, I don't think we are there yet. No, even close to.
Need to run simulations of GMCs, but there's no need for us to run ultimately a simulation
all the way down.
What Andrew was saying. We don't need to run a simulation of cosmological volume that resolves the GMCs. Ultimately, we're going to course grid.
You only need so much dynamic range, you say?
No, but there is a question of predictability of what you're doing, right? So if you throw at your model 20 parameters and you marginalize over and you have a very nice cosmological fit, fine, right? In terms of cosmological parameter estimation, you're happy. And that's the strategy that people are following nowadays, right? They basically marginalize over baryonic physics, right? But I think what we want to understand is to have a predictive model in galaxy formation. And for that, the predictability cannot rely on subgrid models, because subgrid models, by definition, are calibrated on.
But we always have to describe galaxy formation at some point as emergent phenomenology, because we're not going to learn anything new about new physics on the galaxy formation. We know the physics, it's quantum mechanics, it's gravity. At some point, it's emergent phenomenology, and at some point, it means there's a scale below which you're not going to prove the actual physics.
Yeah, but you're doing galaxy formation, so you need to at least resolve the galaxy scales, right? And so that would be to need the scale height of the disk, for instance, and we're far from that. And when you resolve the galaxies, the scale height of the disk, then you resolve the molecular clouds for free. So we're going to need to resolve these molecular clouds, whether we want it or not.
So I want to jump in and take chair's discretion and ask a question. I heard many really great talks about detailed physics of star formation processes doing feedback on regulating star formation. But something that's missing to me is it a solved problem of what actually kills off star formation for good in galaxies? Because in the present day universe, most of the stars are in dead galaxies, and nobody's talking about that. I was just curious.
Oh, we talked about it all week, I thought.
What is it? Is it a solved problem?
We don't know. No.
We don't know. Okay, so it's not. It's an unsolved problem.
Playing with
We're not.
possibilities.
What's the possibility? I've heard very little about AGN feedback, other than maybe we don't need it anymore.
Because that's what we know the least about. But we have them already in all the simulations. Did you see these big, nice bombs going off?
I did.
Well,
Do those kill star formation permanently? No.
they may or may not do it.
The only thing that kills star formation permanently is some kind of maintenance mode feedback. Yeah, so I mean, the basic trick is you only have hot gas, and then you can keep it hot easily with a little bit of feedback, and the only source you have for the relevant kind of feedback is an AGN, because it's so efficient at converting a little bit of mass into a lot of outgoing radiation. But is that what's really going on? We don't know for sure. It's true that the radio energy in clusters is approximately what's needed to make that work.
In clusters?
Yeah, well, that's where you can see it. It may work in ellipticals, but it's hard to see there. But frankly, I think what Avishai said is just the truth. We don't really understand what causes galaxies to stay quenched. It's physically, I mean, it's observed that they do on the whole, but it's not well understood.
Okay, good. Not good, because I came to the meeting hoping I would get the answer.
No, but, you know, I think us simulators, the most important thing to understand is what we don't know and that we might make progress on. And these are all subjects that we don't really understand, but we hope to make progress on in the near term.
So I are people in simulations focusing on that problem? Because I've heard, again, about a lot of regulating star formation, but not snuffing it off, killing it completely.
I think it's really important for the next few years. So supernovae have been a focus for a while, and now people are talking about momentum effects like radiation and other effects like photoionization and so forth that are also clearly very important. Magnetic fields, if you just look at the energy that must be in magnetic fields of 10 microgauss, it's comparable to any other energy in the galaxy. So at least it's going to provide pressure that can't be ignored, but I don't think we understand very well what it does. But then once you're into some mode where the galaxy starts to drop its star formation rate, which does happen naturally in simulations once you put in these other kinds of feedback, the issue of what keeps the galaxy from forming more stars, it can't be star formation because the star formation is already low. So it has to be something else. And that's definitely something that we should understand better, and it's going to require better understanding probably of AGN, but maybe also of other things. So that's, I think, a very important area for research, and I think over the next few years people are going to tackle these questions more and more. So I think these are areas that are very ripe for progress, and I think the reason we aren't hearing too much about it is that a lot of progress hasn't happened yet. But I think all of us know that that's an important topic. So thanks for reminding us.
Thanks, Joe. So if there are no more comments, I want to raise, actually we have two more questions. Oh, okay, so let's go. So the next question is more related to the simulation methodology as a scientific activity. And as you know, science is based on falsifiability, reproducibility, and so on and so forth. And so I've heard a lot of worrying comments on many very complex simulations that has been presented here. For example, when you ask a simulator why he finds this, sometimes the answer is, I don't know, I need a theory to explain my simulation. So that's kind of a worrying kind of comment. What about the robustness of those predictions? We haven't heard a lot about conversion studies, about calibration of feedback model with respect to the resolution they were run on. And that's a very dirty detail, right, that a lot of simulators, including myself, are putting under the carpet. And then the reproducibility of the simulation, I think it's very important. And I'm going to say something provocative, but I think if you really want to use simulation as a scientific methodology, you need to let the other redo the simulation themselves in order to reproduce the results. And therefore, it's the question of open source, free access to the codes, free access to the data. And I see here in the room a lot of people, actually not a lot, I'm wrong, but okay, I see a lot of people who are working with freely available codes, which is good, but some codes are not freely available yet. And my provocative statement is that if you cannot repeat what was published using a code, because you can have access to the code and repeat the calculation, then somewhere the methodology is something wrong, right? So. And so, okay, so the general question is, what about our general methodology in terms of simulation? Are we sure we're doing the right thing? And what would be your reaction in terms of improving on that?
I think open source codes doesn't go far enough. For all the observers here, who here works with archival data? Exactly. We have just as much ability to put simulation outputs on the web as observers have to put big FITS files on the web. And the fact that we're not doing that is another big blow against reproducibility, because we have to trust each other that all of our analyses are telling the things that the paper says that they're actually telling.
No, but you could just put a link to the code on the parameter file and that's it.
but we don't. That's what I'm saying. It's
Yeah,
not being done.
there's no technical difficulty doing that.
Oh, that's true. There's also no technical difficulty open sourcing your code, other than like sustainability issues. Well, yeah, that's. I suppose that there is that technical difficulty. Terabytes are cheap. Terabytes per second are not cheap.
So I should start by saying that I open source more or less everything that I write. Changa that I'm working with at the moment, and Ramses, of course, thank you, Romain, is open source. That said, I think we have to be a little bit careful about what we say here. I mean, it's if you take your experimental analogy, which I think is correct, I think simulations are now. Essentially, we're doing experiments, albeit with a layer of complexity from the fact that, it's not actually reality you're experimenting on, but still, we can think of them as experiments, and we're trying to work towards that. The difficulty is, if you require everyone to be open about everything and to post everything, first of all, well, I guess the main problem with that is you really discriminate against small groups. I'm trying to set up a group at the moment. It's tiny. We simply don't have the resources to do that. We make as much as possible open, and for instance, we'd certainly, we work with open codes. We'd certainly put initial conditions on the web for sure. We will be doing that, but we're not going to make our simulation outputs public because they're huge. And sure, if you're running Illustris and you have a huge army at your command who can make you a super web interface, blah blah blah. Of course you can do that, but if you don't have those kind of resources, then you can't. So I think we have to be really careful that we don't kind of over-legislate about these things.
Well, I just wanted to comment on the Agora policies that I think the steering committee agreed on that have to do with this. You may remember that in his earlier talk today, Ji-Hyun Kim showed initial conditions for the isolated disk and then did not show the results of running those. And the reason is that we all agreed that we want to be open and that we will provide to each other and ultimately to the community a tremendous amount of output, more than 100 stored time steps stored at the same redshifts. And we agreed on which redshifts to store and so forth when we run cosmological simulations. But we also agreed that we're not in the gotcha game. In other words, we don't want to embarrass people. We don't want to force them to reveal results that they're not confident that they're ready to reveal. So what we want to do is have open discussion within the Agora collaboration. So we want people to share results, but not fear that they're going to get embarrassed by those results being released before the authors of them think they're ready. It's a narrow line, but I think it's one that we can follow as long as we're upfront about it and we've agreed on what our procedures are. So the plan is, first of all, just for the isolated disk simulation, a number of groups have looked at what other people have done and rerun their simulations. And until people are happy, and I think they're getting happier with the results, the feeling is we shouldn't force them to release them. The paper, however, is getting close. I think we're going to be finished pretty soon. That's what we're going to be talking about, one of the subjects we're going to be talking about in the next couple of days. So I think this is a workable procedure, and it's a way of not forcing everybody to make everything open, not having open codes, although of course that's very desirable, but it also requires documentation to be useful. But sharing the results of simulations with each other critically, and then releasing them when people feel that they've done what they can. So that's the basic procedure that we hope to follow, and I think it addresses the concern that people are raising. At least I think that's another subject that should be open for conversation. And if not now, then over the weekend.
All right, so thank you, Joel. Let's end. Before we end, let's thank all